All right, we will take a look at section 10.7 Taylor series. In the previous video, we did sort of a visual exploration of what Taylor series actually are used for and giving us an idea and intuition of where they come from. And yeah, so in this case, we're going to take a look at it from more of an algebraic perspective. We do understand that these Taylor series, if you've watched the previous video, they are essentially a way of forming a better and better and better approximation of a function by incorporating information about the function and its derivatives at a single point. This point where we figure out and we extract information about the function, we're really sampling the function at this point. So this point where we extract the information from the function and its derivatives is called the center. And we would say that the series, the Taylor series, is centered at C. Okay, so the Taylor series is this expression right here. So if you have a function f and it is represented by a power series centered at C on some interval with some positive measure, that's what this means. It means we have some interval of convergence, and it is a true interval. It's not actually a single point, because the radius of convergence can be 0, but then we only have convergence at its center, which isn't very useful at all. So we're assuming that we have some measure, some positive measure, some positive width. So we actually do have an interval centered at C, and this goes all the way to C minus R and to C plus R. So we have convergence everywhere in between here. And not just that, but really absolute convergence is what we're going to have on the interior of this interval. At the endpoints, it may diverge. We might have conditional convergence, so on and so forth. Okay, so what we're going to do is take a look at where this formula comes from, why does it have factorials in it, and all that stuff. So what we're going to do is actually focus on this statement right here, and it's if f is represented by a power series centered at C. What does this mean exactly? So if a function f is represented by a power series, centered at C, then this means our function f, the value of f at some x value x, is going to be the result of this convergent power series. So what we're really saying here is that this series converges absolutely on absolute x minus c is less than r, where r is some positive real number. So we're going to assume that this occurs, that this series converges absolutely when we're in this interval of convergence, and it gives us the value of f. So our goal here is, if we're assuming that this function can be represented by a power series, how do we write down this power series? In other words, how do we figure out these coefficients a sub n? Because a power series is uniquely determined by its center and these coefficients. That's what determines the power series. So we want to figure out how, we want to determine what is a sub n. What is that? So if our function is to be represented by a power series, then this means that all the information that we can extract from the function f, we should be equally as well able to extract from the power series itself. So let's just start with some preliminary Yeah, some preliminaries. So if, for instance, we should be able to figure out what, well, we know that this is centered at, let's rephrase that. This series is centered at x equals c. So what happens if we plug in x equals c into the power series? Well, we know that if we plug in x equals c into this, it should spit out f of c. It should. So if we do that, what do we get? We have the sum from n equals 0 to infinity, a sub n, 0 to the n. Well, 0 to the n is just 0. But we should be a little bit more precise because there is one value. Remember, this n is not fixed. This n is varying. So really, 0 to the first power, second power, third power, fourth power, they are all 0. But 0 to the 0 is actually 1. So before we even plug this in, it might be useful for us to think about the power series like this. So if I expand, if I write this series, this right-hand side, if I write this out in an expanded form, we would have a0, this term to the 0, which is 1, plus a1x plus, x minus c, excuse me, plus a2 x minus c squared plus a 3 x minus c cubed plus a 4 x minus c to the fourth, and that's certainly enough to give us the idea of what's going on. So now that we have this nice expanded form, we're just writing this series out in an expanded form. Now we can use we can go ahead and investigate. So for instance, we know that when we plug in c into this right-hand side, if our function f is represented by this power series, then I know plugging in x equals c should give us f of c. It should. So if we plug in c, notice that all these terms will zero out because they have that x minus c factor. So the only thing that survives is this a0. Well, we've just found out what one of the coefficients has to be. A0 has to be the value of f at c. Okay? How could we figure out a1? Well, if we want to figure out a1, what we could do here is take a derivative. So if I find f prime of x, and we can do this term-by-term differentiation, right? Effectively, f prime would be taking the derivative of this power series. And because we're assuming this converges absolutely, this means we can, instead of differentiating the convergent sum, we can first take the sum of the derivatives. We can do that term-by-term differentiation theorem, and we talked about in 10.6 for power series. So this f prime of x, we would have, a1, because this term would zero out to constant. So we would have a1 plus, we'd have 2a2 x minus c plus 3a3 x minus c squared plus 4a4 x minus c cubed. And then, of course, our dot dot dots. So now, if I plug in c here, again, notice that these terms would go to 0, and only the a1 would survive. So f prime of c is a1. So another coefficient we found. And you probably get the idea. We're going to take the second derivative here, 2a2 plus 3 times 2a3 x minus c plus 4 times 3 times a4 x minus c squared plus dot dot dot. Plugging in x equals c again, f double prime, all of these terms zero out, and we're left with 2a2. So 2a2, which implies that a2 is actually f double prime of c divided by 2. F triple prime now is 3 times 2 times a3 plus 4 times 3 times 2 times a4 x minus c. Plugging in x equals c into the third derivative, this term zeroes out, and we're left with 3 times 2 times a3. Which, solving for a3 is f triple prime of c over 3 times 2. Yes, I could write 6, but I'm choosing not to because really, most of you probably can see where this is going. 3 times 2 is 6 factorial. Because although there is not there's no 1 here, I mean, there kind of is, right? We can always just think of everything having a coefficient of times 1 if we want to, because 1 times anything is itself, so we're free to think of it that way if we wish to. Okay, so then lastly, we have our fourth derivative here. So our fourth derivative would just give us, I should have a plus and some dot dot dots there. So 4 times 3 times 2 times a4. Well, there's nothing to plug in here. I mean, I guess technically, because we have some dot dot dots here, I should actually write that. Because whatever's in the dot dot dots here, they definitely have an x minus c term in it. So all of those would also go to 0. So then here, a4 is f quadruple, that's 4 primes, all divided by 4 times 3 times 2 times 1, or whatever. Okay. So there we have it. And we could do this all day if we wanted to. Do this all day if we wanted to. One thing we could do here is notice that the nth derivative of this expression, if I take the derivative of this n times, so let's just grab this expression, a sub n so the nth derivative of a sub n x minus c to the n is n factorial a sub n right? We can test that. What's the third derivative of some number? Let's call it a whatever. Doesn't really matter here. What's really important here is that we have this x minus c cubed. We can just put a placeholder here. We can just call this 3 capital A. It doesn't matter. If I do the derivative 3 times the first derivative, not 3. Let's get rid of that. Sorry. This would be 3 6a x minus c squared, and then another derivative of that. So two more derivatives, I should say. So this is going to be the derivative of 6a x minus c to the first power. The derivative of that is 6a, that's it. And 6 is 3 factorial times that coefficient. So that does check out. This was just a little, sort of a concrete example just to verify that I wasn't off by anything. It's always a good thing to do to make sure you're not forgetting or overlooking something. So the nth derivative of this expression is n factorial a sub n. So let's say since this is the case, then f to the n, the nth derivative, this is n factorial a sub n. So if we plug in c here, so then a sub n is the nth derivative at c divided by n factorial in general. And over here we see that we got all these expressions in the boxes here, which agrees with this more general expression. So now that we know what a sub n is, we can take our generically written power series a sub n x minus c to the n from n equals 0 to infinity, and then if that's supposed to be f of x, we can replace back in what we found that a sub n has to be. A sub n is this nth derivative evaluated at c over n factorial. And that's where these factorials come from and why we have these derivatives appearing. The derivatives are really just a way for us to extract that information to, essentially, we plug in c because we want to eliminate all these terms. And then we take the successive derivatives because we want to not just know what a0 is, but we want to know what the next coefficient, a1, is. Take another derivative so that when we plug in, we get the next coefficient, so on and so forth. So that's more or less where this theorem comes from and why that formula is what it is.